Welcome back to our look at the unit circle. When we had last left off, we had a dozen points, say, right? These 4, and then this point turns into 8 total, so 12 points on the unit circle. And we were trying to find a few more. And so we ended with the question, is 4/5, 3/5, is 0.8, 0.6, is that on the unit circle? And the answer is yes, because that does satisfy the unit circle equation. You can actually plug that in. 4/5 squares to be 16 over 25. 3/5 squares to be 9 over 25, adds together to be 25 over 25, does equal 1. And so that's a way to check and see if something is on the unit circle or not, right? If it does satisfy, then it is on the unit circle. And if it doesn't, like the 0.1/10, 9/10, 0.1, 0.9, that would not be on the unit circle because it does not satisfy the unit circle equation. Something to hold on to as we move forward here. All right, so let's take a moment to see all the points we have so far, right? Because I've got 1, 0, so that would be a point right about here-ish. 0,1's up here, -1, 0's here, and then 0, -1 is down here. So the 1/2, √3/2, that would be 1/2, I guess √3/2 is about 0.866, almost 0.9, so that's up here. And if I were just to draw all of them, they would look something like this. Pardon my poor mouse control. It would be something like that. And we're probably not ready to admit that this is a circle yet. I mean, this looks like a very poorly drawn diamond right now, as much as it does a circle. So we might want more points, we might not, but I would say let's just dispense with finding more and more points. We could do it, we could find more and more points, but let's look at it another way. Right, the equation we have here is x squared plus y squared equals 1. Oh, let me hide that. X squared plus y squared equals 1. So if I were to take the square root of both sides, I would have 1 equals root x squared plus y squared. But that's actually the distance formula. Specifically, the distance formula saying every x, y, right, every point that is 1 away from 0, 0, 1 away from the origin. This actually forms a circle, radius 1, centered at the origin. This is our unit circle equation. And so, henceforward, we will refer to x squared plus y squared equals 1 as simply the unit circle, and this equation is simply the unit circle equation. So that's what we're going to be doing going forward here. So now comes the issue that I had alluded to earlier, which is moving on the unit circle. So if we're going to make x squared plus y squared equals 1, if we're going to make that circle our whole universe, then if you were to be on that circle moving, you have one of two options. You can either move clockwise, or you can move counterclockwise along it. And traditionally, if we had to call anything a starting point, because the origin is gone, right? The origin is not in the unit circle. We usually make the point 1, 0 our starting point. That's our new origin, if you would call it that. And so, let me show you what moving on the unit circle looks like before we really get into the details here. That's our unit circle on Desmos here. We have a graph with a circle radius 1 centered at the origin. And, let's see, let me scoot this in a little bit. There we go. That's my equation. X squared plus y squared equals 1. And that's all the points on it. But let's take the specific point 1, 0. That's my starting point. And what I mean when I say moving around the unit circle is I mean exactly that. As we move counterclockwise, as we move in what's henceforward known as the positive direction, we just move around the unit circle. That's all I mean. That's all I mean by that. Now, you can move clockwise, but that would mean moving in the negative direction. Clockwise is negative, counterclockwise is positive. And the starting point's 1, 0. These are just things that we're going to have to hold on to because that's just the way it is. And I'm sure I could really, if I wanted to, dig up the history of math as to why, but I'd probably just find that whoever started this, that's what they chose. And that's just the way it is. And that's all we need to worry about. Now then, since the circle has a radius 1, that means it's of circumference 2 pi, right? 2 pi r is the circumference of a circle. So if I go around exactly 2 pi. If I go around exactly 2 pi, I'm going to end up exactly where I started. If I go exactly 2 pi, that's the decimal approximation, I'm going to end up at 1, 0 again. And of course, I can go around again. 4 pi would end me up at the same spot. 8 pi would end me up at the same spot. 6 pi, I guess, I don't know why I skipped 6 pi, but 6 pi would also end me up at that same spot, 1 comma 0. Now, if I went negative 2 pi, or negative 4 pi, or negative 6 pi, right, I'll go around once, twice, or 3 times. That would also end me up at the point 1 comma 0. That would be my so-called terminal point. Of course, that's not the only place I could end up, right? Let's say I moved pi instead of 2 pi. Well, that would get me halfway around the unit circle, right? If the whole thing's 2 pi around, then half that would be a semicircle. I would go half the distance, so I would end up at the point negative 1 comma 0. Of course, I could do half of that again, move pi over 2, and that would spit me out at the point 0 comma 1. Right? That would be 1/4 of a full rotation around the unit circle, 1/4 of a full trip. And so I would go 1/4 the circle. I would end up at 0 comma 1. Incidentally, right, these are the points that we had found already. Now, let's see here. 3 pi over 2, that would put me down here. And you see now we can do pretty much anything. And that will get us. Actually, we can do anything. Any real number will get us some point on the unit circle. More to the point, any and all real numbers together, right, using all real numbers, that would give us every point on the unit circle. So let's see here. Let me trash this. So here's my point, and I can get to any point on the unit circle just by moving some distance along the unit circle, call that distance t, and that would get me any arbitrary point on the unit circle, and by extension, every point on the unit circle. So here's back to the details. Here's our details. We start at 1 comma 0. We move some distance on the unit circle where counterclockwise is positive, and that ends up at some terminal point. And every point on the unit circle can be expressed as a terminal point from moving from 1 comma 0 some specified number, some specified distance, where that number is the distance. So what we have left to do, because we've now got ways to get these 4 values on the axes, we need to start worrying about where and how we get anything else in between. So here's my question to you. Suppose I start at 1, 0, and I move 11 pi over 2 in the counterclockwise direction, right, because that's positive. Where am I going to end up? Am I going to be in quadrant 1, quadrant 2, 3, or 4? I don't need the exact coordinates. We'll actually find the exact coordinates in the next video. But where generally am I going to end up? So, recognizing that 2 pi is a full revolution, and 8 pi, let's see, 2 pi is 8 pi over 4. So it looks like we're going a little past a full revolution here. Where generally am I going to end up? What quadrant? You tell me that, and then I will see you in the next video. We'll wrap up this unit circle business. See you then.